I'm going to do an example of a two-dimensional kinematics problem. Specifically, this is a projectile motion example. Frogs have an amazing ability to jump incredible distances. One of the most impressive jumpers, the South African sharp-nosed frog, can jump up to 44 times its length. That would be like a human being jumping 3/4 of the way across a football field. So let's say that you see a frog and it leaps at an angle of 30 degrees from the ground and jumps forward 3.0 meters. We want to find out how fast was that frog going when it took off. Whenever we want to solve one of these projectile motion problems, a good place to start is to draw a picture. So here's a picture of our frog jumping at some initial velocity v initial, which we don't yet know, and it leaves the ground at an angle theta from the horizontal, and we know that theta is equal to 30 degrees. Then we know this frog is going to take a nice parabolic path, and it's going to land 3.0 meters from where it started. And our job is to figure out how fast this frog was going when it leapt. One of the most important insights that you can have when solving a projectile motion problem is to realize that the horizontal and vertical motions are independent. In other words, even though gravity is pulling the frog downward, that doesn't affect how the frog is moving in the horizontal direction. So why is that important to us as problem solvers? Well, if the horizontal and vertical motions are independent, that two-dimensional problem that looks pretty complicated is actually just a combination of two simpler one-dimensional kinematic problems, one in the horizontal direction and one in the vertical direction. But there's one piece of information that ties the horizontal motion and the vertical motion together. Do you know what that is? It's time, because the frog travels vertically for the same amount of time that it travels horizontally. So whenever you see a projectile motion problem, you should be thinking about vectors, and whenever you think about vectors, you should establish a coordinate system. I'm going to say that where the frog started will be the origin, and just so that I don't crowd out this picture too much, I'm going to draw the coordinate axes over here, and I'm going to say that the positive x direction points to the right, and the positive y direction points upward. Now, when you look at this initial velocity, you can sort of see that it's going up and to the right. In other words, you can break this velocity into two components, a horizontal component and a vertical component. So this horizontal component we're going to call the initial velocity in the x direction, and this vertical component we're going to call the initial velocity in the y direction. Since this is a nice right triangle, we can use trig functions to find the relationships between the sides, the Vix and the Viy, with the initial velocity and this angle theta. So I know that cosine of theta is equal to the adjacent over the hypotenuse. So here, the adjacent side is V initial x, and the hypotenuse is Vi. So if I multiply Vi by both sides, I find that the V initial in the x direction is Vi times cosine theta. So this, I can fill in right here, Vi cosine theta. Similarly, I know that the sine of this angle theta is equal to the opposite, which is Viy, divided by the hypotenuse, which is Vi. And again, if I multiply Vi by both sides, I get Vi sine theta equals Vi in the y direction. So I can plug that in over here. The next thing we want to do is to figure out what's going on with the accelerations. So the obvious one here is what's going on in the y direction. So I know my acceleration in the y direction is due to gravity. And since gravity pulls downward, but I said that upward was the positive y direction, then I know my acceleration due to gravity is just minus g, because it's going in the opposite direction, which is just minus 9.8 meters per second squared. So what about the acceleration in the x direction? Well, we know that air resistance is negligible, so we don't need to worry about that. But would there be anything else that would accelerate the frog in the horizontal direction during its flight? You might be tempted to say something about the frog pushing off the ground, but that happened before the frog was in flight. As soon as the frog is in the air, its toes are no longer on the ground, and so once it's in the air, the only force acting on it is gravity. So we can say that the acceleration in the x direction is 0 meters per second squared. Now that we have some basic information down, let's try to see if we can solve this problem. Remember, we want to break this down into two parts. What is happening in the horizontal direction, and what's happening in the vertical direction. So our generic kinematic equation for the horizontal position would just be x final equals x initial plus v initial in the x direction times delta t plus 1/2 times the acceleration in the x direction times delta t squared. Now, of course, these times refer to the time of flight. So let's figure out what we know. We know that the frog starts at the origin, so its x initial position is 0. What about the x final? X final measures the position along the x-axis where it lands. So that would be 3 meters. Okay, so I'm going to go ahead and write that here. Now I know that the acceleration in the x direction is 0, so that term goes away. And this equation just cleans up to x final equals v initial in the x direction, which I now know is vi cosine theta, times delta t. All right, so this is looking a little bit simpler, but I don't know vi and I don't know delta t, so it looks like I have two unknowns and only one equation. So I need another equation. Where is that going to come from? From the vertical stuff. So now I can use my generic vertical equation, which is yf equals y initial plus v initial y delta t plus 1/2 a y delta t squared. All right, so again, if the frog starts at the origin, then I know y initial is 0. And what about y final? Well, when the frog landed, even though it was far away and even though it went up and down, y final is just referring to its y position when it lands. So you can see that its final position is on the ground, which according to our coordinate system is where y equals 0. So this term also goes to 0. This gives us 0 equals VIY times delta t, and I know my VIY is just VI sine theta times delta t plus 1/2, and my acceleration in the y direction is of course minus g, so I'll put that in here, times delta t squared. Okay, and I'll just go ahead and move that negative sign out front. So you can see here that this is a quadratic, but since the constant term is just 0, we don't actually have to do the full quadratic equation to solve this. We can go ahead and just add this 1/2 gt squared to the other side. So we have 1/2 g delta t squared equals vi sine theta times delta t. Here you can see that one of those delta t's cancel. That's actually the t equals 0 solution to the quadratic, but that's not really important to us because t equals 0 means, yes, it was at y equals 0 at t equals 0, but that doesn't tell us anything about what was happening during the flight. So now we can actually solve for the time, and we have delta t. I'm going to multiply both sides by 2 and divide by g. So delta t becomes 2 times vi sine theta over g. And now I can plug this delta t in for the horizontal equations. So let's go ahead and do that. All right, and I'll go ahead and clean that up a little bit. So x final is, looks like you had a vi squared times 2 cosine theta sine theta over g. And of course, what I'm actually looking for is this v initial. So I'm going to basically multiply by g and divide by 2 cosine theta sine theta, and I get v initial squared equals gxf divided by 2 cosine theta sine theta. And that is my symbolic answer if I take the square root there. But if we want to plug in numbers, we see that that is 9.8 meters per second squared times 3.0 meters. And we have a 2 cosine theta sine theta under the square root. And this gives us 5.8 meters per second. You know the unit is meters per second because on the numerator you have a meter squared times a meter squared divided by a second squared, and there's no units on the bottom. So the square root of meter squared over second squared is meters per second. So the initial velocity that the frog leapt with was 5.8 meters per second. So even though we only had the angle and the distance the frog traveled, we could figure out the initial velocity, which I think is pretty cool.